In this video, I'm going to cover chapter 4 of my stochastic modeling book. That's the chapter about the basics of stochastic processes, including definition and examples of martingales and Markov chains. More precisely, here are the different topics we are going to cover in this video, but also the next videos, along with all the logical connections. As usual, in case you are interested in one specific part of this video, check out the description of the video or the thumbnail of the video with the specific timings, and so you can jump directly to the part you are interested in. So first, I'm going to define the general concept of stochastic process and related notions that we call state space, sample path, and realization. In case your stochastic process evolves in time, which is the most typical type of stochastic process we see in practice, another important concept behind the notion of stochastic process is the concept of filtration. A filtration is basically a sequence of sub-sigma algebras of F that I'm going to call Gn. And you can think of Gn as the amount of information you know at term n. So that's basically everything you learned from term 0 to term n. I'm going to call that the sigma algebra of the past and present. Okay? And this concept is important to define the notion of martingales and Markov chain. So, more precisely, a martingale, or also related processes called sub-martingales and super-martingales, are defined from looking at the conditional expectation of the future given the sigma algebra of the past and present. Okay? That's how we define a martingale. The definition is a little bit dry, but I'm going to give you the intuition behind the definition, and using this intuition you can often guess whether a process is indeed a martingale or not. So basically you can think of a martingale as a stochastic process modeling a fair game. Alright, so the concept of martingale was introduced by Paul Levy, but most of the early results in martingale theory were proved by Joseph Joubert. Then we look at the concept of Markov chain. Like for martingales, Markov chains are defined from looking at the filtration, but in combination not with the conditional expectation, but with conditional probabilities. In particular, the process is defined by looking at conditional probabilities of typical events in the future, which is unknown, random, given the sigma algebra of the past and present, which is known. Alright, so that's how we define a discrete time Markov chain. I'm also going to give you some intuition behind the definition, and we'll see that a Markov chain is basically a stochastic process that is memoryless, meaning that to make prediction about the future of the process, given past and present, you can only use the present information, you can forget the past. So that's some kind of memoryless property. The concept of Markov chain was introduced by Markov, and many of the results in the field were proved by Kolmogorov also. Alright, so then after I'm going to look at different examples. The 4 examples here. For each of those 4 examples, we are going to check whether the stochastic process is or is not a martingale and or a Markov chain. In particular, to check whether those processes are martingales and or Markov chain, we need to use the techniques I covered in chapter 2, in particular about the conditional expectation of a random variable given a sigma algebra when this random variable is measurable with respect to the sigma algebra or independent of this sigma algebra. These are 2 important properties we saw in chapter 2. That's those properties we are going to use today to check whether each of those 4 processes is a martingale or is a Markov chain. So more precisely, the first example is just a sequence of independent coin flips of a fair coin. The second example is a very popular stochastic process in probability theory called the symmetric random walk. I'm going to look at the symmetric random walk on the integers. The next one is called the Belling random walk. That's some kind of nice variation of the symmetric random walk that is used to model games, like games at the casino. And then the last example is something I'm going to call the two-coin process. That's more or less the same as the first process, but using two biased coins instead of one fair coin. So those models are designed to show that the concept of martingales and Markov chain do not imply each other, but do not exclude each other either. In particular, among those four examples, one is both a Markov chain and a martingale. Another one is a martingale but not a Markov chain. Another one is a Markov chain but not a martingale. And the last one is going to be none of the two. Okay? That's to show you that the four possibilities happen, and that's how those four examples are designed. Okay? Then that's going to conclude this video, but I also have some connections with future videos, so I can give you an overview of what we are going to do in the future. Chapter 5 is about martingales. Today I'm only going to give you the definition of a martingale and some examples of stochastic process. And for those stochastic processes, we are going to check whether we have a martingale or not. But I'm not going to cover all the properties of martingales. In chapter 5, we are already going to look at all the properties of martingales, in particular the optional stopping theorem, upcrossing inequality, martingale convergence theorem, and all the convergence theory about martingales. Okay. Then chapter 6 is about Galton-Watson branching processes. Those processes are important in biology. They model the dynamics of population, but they can be viewed as more general, like invasion model, that can be used outside the field of biology. We can think of chapter 6 as an application of chapter 5 in the sense that to study those processes, you need to use results from martingale theory. So that's going to be an application of chapter 5. Then chapter 7 is about discrete time Markov chains. So same as for chapter 5, I'm not going to only give you the definition. We are going to look at all the theory of discrete time Markov chain, including recurrence, transience, irreducibility, positive recurrence, heterodycity, the notion of stationary distribution, and all the convergence theory about this type of processes. Okay, so that's going to be chapter 7. Chapter 8 is about random walk, and exactly like Galton-Watson branching processes is an application of martingale theory, this chapter is going to be an application of chapter 7. Okay, so by random walk here, I don't mean just the symmetric random walk on the integers we are going to study today. I mean really like very general random walks that evolve on a general connected graph. Okay? And for those processes, we are going to study the notion of recurrence, transience, but also some interesting connection between those processes and electrical networks in physics. Then chapter 9 is about Poisson processes. The main three properties about Poisson processes, but also Poisson point processes that I'm also going to cover are the superposition property, the thinning property, and the conditioning property. We are going to prove all those three things when we cover chapter 9. Finally, chapter 10 is the one about continuous time Markov chain. And one important result we'll see in this topic is the fact that under some conditions, a continuous time Markov chain can be viewed as the combination of a discrete time Markov chain that keeps track of the sequence of states visited by the process and a collection of Poisson processes that keep track of the times at which the process jumps. First, let's look at the definition of a stochastic process and the notion of filtration and the intuition behind those two different notions. So, first, a stochastic process is just a collection of random variables, xi, all defined on the same probability space omega fp. So you have in the background a single probability space, and we value in a set S with its Borel sigma algebra. So I want to point out that this collection is basically of the form xi for I belonging to a general set capital I. This set capital I can be anything that can be finite, countable, uncountable, that can be a one-dimensional set or something in higher dimension. Okay. Then also, what do we mean by the Borel sigma algebra on the set S? At the very least, we need to assume that S is a topological space, in which case the Borel sigma algebra on S is going to be the sigma algebra generated by the open sets. But in general, in practice, S is just a subset of R, in which case the Borel sigma algebra on this set is just the one generated by the intervals like we defined in chapter 1. If S is finite or countable, is a finite or countable subset of R, in this case, the Borel sigma algebra is just the set of all the possible subsets of S. Alright, so that's what we mean by a stochastic process. That's any collection of random variables defined on the same probability space. Now, a few more definitions. The set omega is called the set of realizations of the process. In the case of probability theory, we said that omega is the sample space and it corresponds to the set of all the possible outcomes of an experiment. Now, instead of using the word outcomes, we use the word realizations, but outcomes and realizations are more or less the same thing. It's just the word we use in the context of stochastic processes. Then, next definition, this set S here is called the state space of the process. That's the set of all the possible states or possible values those random variables can take, all right? And then a third definition that's kind of interesting is to motivate the definition, just look at really the definition of a stochastic process. So that's a collection of, a very general collection of random variables or measurable functions. If you fix a little I in capital I, then what you do is you extract from your process one single random variable. Another thing you can do, because they are all defined on the same set omega, is instead of fixing a little I in capital I, you can fix a little omega in capital omega. So you fix one realization. And in this case, if you look at the value of xi, but at all those points, instead of having a collection of measurable functions or random variables, you end up with a collection of elements in S. This collection is called a sample path. And sometimes I'm going to use the word realization of the process instead of sample path, just because to fix a sample path, more or less what you have to do is just fix a realization omega in capital omega. Okay? So each time you fix a realization, then implicitly you can look at the value of those functions at this realization omega, and you fix a sample path. So realization induce sample path, and so the two are related in this sense. So now I want to point out that when you write a numerical simulation of a stochastic process and you run your program, then what you see, the output you see, are not strictly speaking, is not strictly speaking the stochastic process, but these are sample paths of the stochastic process. Now, if you run your program enough, okay, then you see a lot of sample paths or a lot of realization of your process, and that gives you a good idea of how your process behaves. But strictly speaking, you cannot see a stochastic process, you cannot visualize that. That's an abstract concept, that's a collection of measurable functions. when you run a program, the only thing you see are sample paths, not the stochastic process itself. All right. So now I want to come back to vset I. I told you vset I can be anything, but most of the time in practice, the set I is going to use to model a temporal structure. Okay? So eventually, instead of having a collection of random variables, you have a sequence of random variables indexed by basically a set with a total order, and you have something that evolves in time. But it's also possible that your set I is more general, and some stochastic processes do not evolve in time. So examples of such stochastic processes would be all kinds of random graphs. So for instance, Erdős-Rényi graphs, scale-free networks, and so on, if you heard about that. A random graph or complex network is basically a static object. That's not something that evolves in time, but that's a random structure that is obtained by looking at a collection of random variables. And so strictly speaking, those mathematical objects are still stochastic processes, even if they do not evolve in time. Okay, so in this video, I'm going to only focus on things that evolve in time. Martingales and Markov chain are stochastic processes with a temporal structure. So how do we use vset I to model a temporal structure? Well, first have in mind that, for us, human beings, time is a one-dimensional thing, is a one-dimensional space, and time can only go in one direction. So that means that if you take a little I in capital I and think of this little I as time, then everything that is smaller than I would be interpreted as the past, what happened or all the times before time I, but everything that is larger than I would be interpreted as the future, that is still random, that is still unknown. So what I mean is that because in our mind, time is a one-dimensional space and time can only go in one direction, then we have this notion of past, present, and future. The only way you can have those notions of past, present, and future is if you assume that I is a set equipped with a total order in which you can order the elements. So you indeed have the past that is before, that is smaller than the future. All right. So in practice, we have two natural choices for I when we want to model evolution in time. I can be the set of non-negative integer, in which case we have discrete time, what we call discrete time, or I can be the set of non-negative real numbers, in which case we deal with continuous time. Okay? So discrete time means that now the possible times are 0, 1, 2, 3, and so on. Okay? And so your stochastic process here becomes, let's say, xn for n larger or equal to 0 integer. And so your process is basically a sequence, x0, x1, x2, and xn in general represents the state of the process at time n. You can do the same in continuous time. You just assume that now instead of a collection xn where n is in this set, you have something that we typically call xt, where t is larger or equal to 0, and xt represents the state of your process at time t. T can be any positive real number. So now we have a total order on those two sets, so which means that we have the notion of past, present, future. If n in discrete time is the current time, then every integer non-negative but smaller than n are interpreted as the past, and all the integers strictly larger than n will be interpreted as the future. Alright, so in this video now I'm going to focus on the discrete time case. So that means in particular that I'm only going to define the concept of martingales and Markov chains in discrete time. But you can define the same classes of stochastic processes in continuous time. The definitions are basically the same. It's just that things are a little bit easier to conceptualize in discrete time. All right. So, in case you have discrete time, something that evolves in discrete time, or at least that in general that evolves in time, an important notion that you have in the background behind your notion of stochastic process is the notion of filtration. And so a filtration is defined as a non-decreasing sequence Gn of sub-sigma algebra of F. And we are going to interpret for each fixed n, we are going to interpret Gn as the information available at time n. So have in mind that if you see your process from time 0 to time n, then the past is now known, you saw it, and it's fixed, it's deterministic. At the opposite, the future is unknown. That's the random part. That's the thing you don't know yet, okay? And so Gn basically just tells you, you know everything that happened between time 0 and time n, but you don't know the future. Of course, as time evolves, then you accumulate more and more information, okay? And so that's why we assume that a filtration is a non-decreasing sequence of sigma algebras, non-decreasing because as time evolves, you know more and more, and so your sigma algebra, they contain more and more information, and so they are larger and larger. All right, so then next definition, we say that the process Xn, so you see that this collection here, because now we assume that capital I is equal to n, that becomes Xn for n, an integer larger or equal to 0. I'm going to write just Xn for short like that. But this is a notation to say the collection or the sequence x0, x1, x2, xn, and so on. Then we say that the process Xn is adapted to the filtration Gn if for all n, Xn is Gn measurable. So remember in chapter 2, we saw that Xn Gn measurable means that if you know Gn, then you know Xn. So based on that, the interpretation of Xn is adapted to Gn is the fact that the process itself is part of the information available. If you know Gn, so everything you know up to time n includes the evolution of the process or the sample path of the process from time 0 to time n. That's what it means that Xn is adapted to Gn. So in practice, we don't use a very general filtration. In general, we use something simpler than just what we call the natural filtration. The natural filtration, so is the sequence Fn of sub-sigma algebras of F, and in general, Fn is the sigma algebra generated by the random variable x1, x2 up to xn. Alright, so notice that because this sigma algebra is generated by a bunch of random variables including xn, that means that if you know Fn, then you know xn. Okay? So, in particular, any stochastic process is adapted to its natural filtration. Okay, so that's one first observation. Notice also that Fn is indeed a filtration. These are sub-sigma algebras of F, and at each time step you add more random variables and so more information. So indeed, this is a non-decreasing sequence of sub-sigma algebras, and Xn is adapted to Fn. Notice also that by design, okay, the amount of information we put in Xn is exactly the information contained in the process. And so you can think of the natural filtration as the smallest possible filtration the process Xn is adapted to. That's typically the filtration we use in practice. All right, and so, like I just explained, interpretation of the natural filtration. The natural filtration corresponds to the information available when only the process is known. You don't have any other process in the background running that is part of the information. The only thing you can observe is your process itself. Now let's define the notion of martingales and related stochastic processes called sub-martingales and super-martingales. So in the discrete time setting, your process is like this, is written like that, it's xn. We say that the process xn is a martingale with respect to a filtration gn. So you need a filtration in the background. If for all n, xn is in L1, so that means that all those random variables xn are integrable, and the stochastic processes xn itself is adapted to the filtration gn. Remember that what this means is that if you know gn, you know xn, and another way to think of that is just to say that at time n, you know what happened in the process, so that means that at time n, you know x0, x1, x2, up to xn. What happened in the process is part of the information available. Very often in practice, we say that xn is a martingale without specifying the filtration. In this case, what we mean is that the process xn is a martingale with respect to its natural filtration. When the filtration is not specified, we mean the natural filtration. The most important condition is the second one here in blue. That's the one we use to prove theorems, properties about martingales. It says that the expected value of xn plus 1 given gn is equal to xn for all n. So what this means is that regardless of what happened in the past, including the present, what you can expect at the next time step is on average the same as what you see right now. And so for this reason, that helps to think of xn as the fortune of a gambler playing a fair game. I'm going to display that. If you think of xn as the fortune of a gambler playing a fair game, so martingales means fair game, then indeed you should have this relationship. That means that no matter what was your fortune at time 0, 1, 2, 3 up to time n, if you play the game one more time, and by n, time n, I mean the number of times you play the game, then regardless of what happened in the past, of how your fortune evolved in the past, on average what you are going to have after playing the game one more time should be equal to the amount of money you have right now. Okay? So martingales means fair game. Of course, many stochastic processes in practice are martingales and they do not model the evolution of the fortune if you play a fair game, but still that helps to have this interpretation in mind, to have a good intuition on the way the process is going to evolve. So let's look at that in a picture now. Here I have a picture of the sample path of the process from time 0 to time n. So that's basically what you know, that's the information you know at time n, assuming that gn is just equal to the natural filtration. You don't have extra information, you know exactly that. Saying that you have a martingale would mean that on average, at the next time step, at time n plus 1, you are going to be at the same level as here, okay? And so that means that you have basically some mean zero increments, okay? So the part of the trajectory or sample path in black is basically what happened in the past, that's fixed, that's deterministic. Now, the white here, all the white points are, let's say, all the possible futures. What can happen after you play again the game one more time. And then what you want is that on average, where you are going to end up is the same as xn itself, so the level of this black point here. That's what we mean by a martingale. Fair game means zero increment. All right, so now let's define the notion of sub-martingales and super-martingales. Sub-martingales and super-martingales also satisfy the first property here, but the second property is relaxed. Instead of having equal, for a sub-martingale you have a larger or equal than, and for a super-martingale you have a less or equal than. Okay? And so, same story as for martingales. You can think of sub-martingales and super-martingales as processes that keep track of your fortune if you play a game. But in the case of sub-martingales, the game is favorable because regardless of all the possible past, on average, what you are going to have at the next time step is larger or equal than xn. At the opposite, a super-martingale is going to be a model for an unfavorable game where you are more likely to lose than to win on average. Given all the possible past, the expected value of your fortune at the next time step is going to be less than what you have right now. Just one last comment. The reason we call those processes sub-martingale and super-martingales are because the notion of sub-martingales is related to the notion of subharmonic function, while super-martingales are related to superharmonic functions. Now let's look at the definition of a discrete time Markov chain. So here is the definition. We say that the process xn is a discrete time Markov chain with finite or countable state space S. Assuming that the state space is finite or countable is typical in practice for at least discrete time Markov chain. So if we have the following equation, the probability, the conditional probability of that xn plus 1 is in a set B given Fn is equal to the probability of the same event xn plus 1 in B given only xn. This should be true for all subsets B of the state space S. Notice that because the state space S is finite or countable, any subset of S is going to be a Borel set. Okay? So, for this reason, xn plus 1 in B is indeed the pre-image of a Borel set by the random variable xn plus 1, which is measurable, and so this set here is indeed an event. So we can indeed look at the conditional probability of this event. This event, because B can be anything, is a typical event in the future at time n plus 1. What I mean by that is that any event happening at time n plus 1 must be of this form, must be of the form xn plus 1 in the set B. What this equation tells you, basically, is that if you look at any possible event in the future, the probability that this event happens, given that you know the past, all the past and the present, is equal to the conditional probability of the same event, but only given the present. What this means is that to estimate the probability of something happening in the future, you do not need to know all the past, you only need to know the present. Only the present is relevant, okay? And so eventually the intuition behind the notion of discrete time Markov chain or even Markov chain in continuous time is this notion of memoryless that we can express saying that the future of the process depends on the past only through the present. And another a little bit more fancy way to say the same thing is to say that given the present, past and future are independent. So again, that's this idea of memoryless. If you see the process from time 0 to time n, and you have knowledge of all that sample path of the process, to estimate the probability of something happening in the future, you can just forget all the past and only remember the present. The process is going to forget the past and only have in mind the present. That's a good way that's the good intuition behind the notion of Markov chain. So, looking at, again, this definition and the interpretation in picture, I again have exactly like here, let's say a sample path of the process from time 0 to time n. Let's assume that we are right now at time n. And so all the black dots here is what we know that represents basically this sub-sigma algebra Fn. That's our knowledge of the past. And then what this property says is that to estimate the probability of something happening in the future, so the probability that the process is going to jump here. Now the white dot is unknown, that's only one possible future. Then the probability that indeed we jump to this point depends only on our position at the current time. And you can just forget all the past of the process. Okay? That's the first interpretation. The second one, which is mathematically equivalent, says basically that assuming that you let the process evolve more and you have, let's say, a wide trajectory in the future, then given only the state of the process at this time n, then the black part of your sampled path, excluding this point, and the white part of the trajectory are both going to be independent, given that you know where you are at the current time n. Now let's look at our 4 examples of stochastic processes starting from this sequence of independent coin flips. So more precisely, the definition is here. I'm going to call the process Wn, and we start with a fair coin, so that comes up with heads or tails with the same probability 1/2. We assume that consecutive coin flips are also independent. The process is defined by just saying that if, at each unit of time we flip the coin, if at time n we get heads, then we set Wn equals +1, but if we get tails, then at this time Wn is equal to -1. So this process is not the most exciting because those random variables Wn are independent, which is a very strong assumption, but we can use this process later to generate the symmetric random walk on the integers and the Belling random walk. So the main objective now for this process is to check whether this process is a martingale or a Markov chain. And to prove those, we need to obviously use techniques that we saw in chapter 2, looking at conditional expectation of a random variable given a sigma algebra and decomposing basically this random variable in the future as a part that is fully known, so completely in the past or present, and a part that is completely unknown, independent of past and present. That's the typical technique we use to prove that a stochastic process is a martingale or a Markov chain. So let's look at first whether this process is a martingale. Without doing any calculation, intuitively, it doesn't matter what were the outcomes of the coin flips between time 1 and time n. The next coin flip will be on average 0, okay? Because regardless of the past and even the present, at each time step we get +1 or -1 with the same probability 1/2. So the expected value of Wn is 0. And clearly, the future does not even depend on past or present because the coin flips are independent. So what we expect is that given the past and the present, the conditional expectation of Wn +1 in the next time step in the future should be equal to 0. Okay? But Wn is never equal to 0. That can be larger, equal to +1, or smaller, equal to -1. which suggests that Wn is in fact not a martingale. It's in fact not either a sub-martingale or a super-martingale. And the proof is here that just again using basic properties that we saw in chapter 2, what we are using is the fact that Wn plus 1 and Fn are independent. So what is that? Fn is the filtration, and so this for this particular n, Fn is going to be the sigma algebra generated by W1, W2, and so on up to Wn. But all those random variables are independent by assumption. Okay, so this means that Wn plus 1 is independent of W0, W1 up to Wn, and so Wn plus 1 is independent of Fn. Using techniques that we saw in chapter 2, that says that basically the conditional expectation of a random variable given a sigma algebra is just equal to the unconditional expectation of this random variable if the random variable and the sigma algebra are independent. Using this property, we can write that the expected value of Wn plus 1 given Fn is just equal to the expected value of Wn plus 1. Basically, Fn does not give you any information about what's going to happen at the next coin flip. Okay? So this is just equal to expected value of Wn plus 1. And clearly, this is equal to 0. Okay? Because you get plus 1 or negative 1 with the same probability 1/2. And obviously, that's not larger or smaller than Wn. Wn can be plus 1 or negative 1. So conclusion, this process Wn is not a martingale. Even if this is a very basic example, that's important because what we will see in the future is the fact that if a process is a martingale, then by using basic properties of the conditional expectation, you can prove that the expected value of your process should be constant. But this provides a counterexample showing that the converse is not true. It's possible that a stochastic process has a constant expected value. That's the case here. Expected value of Wn is always equal to 0, and still the process is not a martingale. All right. Now, next step, is it a Markov chain or not? Well, the answer is yes. In fact, that's a degenerate case of a Markov chain in the sense that given the past and the present, the future does not even depend on the present because things, again, are fully independent. Okay? So, given past and present, the probability of events in the future are equal to the unconditional probability, even if you do not know the present. And so that gives you a case of Markov chain this time, but that's, I would say, a degenerate case where your conditional probability does not even depend on Wn in this case. And the proof is about the same as here. We again use independence to say that the probability of Wn plus 1, that Wn plus 1 equals 1 given Fn, is equal to the unconditional probability that Wn plus 1 equals 1. For that, I'm using the fact that this event is Wn plus 1 measurable, but Wn plus 1 is independent of Fn. So this event and all events in Fn are independent. Properties of the conditional probability given a sigma algebra tells us that this conditional probability is just equal to the unconditional probability. But clearly, the probability that Wn plus 1 equals 1, which is, by the way, I didn't precise, but that's a typical event in the future. You have this one or equal to negative 1. The proof for equal negative 1 is exactly the same. So the probability that Wn plus 1 is equal to 1, that's exactly the probability that you flip the coin and get heads, which is 1/2. So you get this 1/2. But then using the exact same reasoning, you can also say that the probability of Wn plus 1 equals 1 given Wn, because Wn plus 1 and Wn are independent, okay, by assumption. That's a very strong assumption. In this case, you have also that this conditional probability is equal to the unconditional probability that Wn plus 1 equal to 1, which is also equal to 1/2. And so eventually, you get that the probability of a typical event in the future at the next time step, given Fn, is equal to the probability of the same event but given only Wn. Conclusion, we have a Markov chain. So this example shows in particular that Markov does not imply martingale. Now let's look at our second example, the symmetric random walk on the integers that we are going to study further when we cover chapter 8. So I'm now going to call the process xn, and you can think of xn as the position of a particle at time n that jumps right or left with the same probability 1/2. So here I have a picture of the integers. What this means is that if your particle is here at time n, then at the next time step, that's going to be on the right with probability 1/2 or on the left with probability 1/2. Okay, that's just the way the process is defined. Here are some examples of realizations or sample paths of the process. You have 3 of them with 3 different colors. Okay, so here time goes from time 0 to time 400, and each of those random walks or particles start at position 0. Okay, and so you can go, each time you go up here, that means that you increase the position, so that corresponds to jumps to the right, while when the trajectory goes down, that corresponds to a jump to the left. Then, the way you can simulate this process is basically by starting at 0 and flipping a fair coin. You flip a fair coin, each time you get heads, then you go up, each time you get tails, you go down. Or in the picture where you have the particle on the horizontal line, that means that each time you flip the coin and you get heads, then you move the particle to the right. Each time you flip the coin and you get tails, you move the particle to the left. Okay? And so, another way to visualize the process is just by replacing those probabilities 1/2, 1/2 by heads and tails, by using the same fair coin as in the first example. Okay? That's what I mean by you can generate this process xn by using the previous process that we studied already, Wn. Okay, so in fact, you can in general write your process xn that way. Xn can be written or is equal in distribution to x0, the initial position of the particle, plus W1, plus W2, and so on up to Wn. That's the way you can generate the process. You start from position x0, you flip your fair coin, okay? If you get heads, then your W1 is equal to +1, which means that at time 1 your particle is at position x0 +1. Or you can also get tails with probability 1/2, in which case your W1 is equal to -1, and the position of the particle at time 1 is going to be the initial position -1. Okay? And you can keep flipping the coin, and at each time step that's going to give you like the increment, whether the particle goes to the right or to the left. All right. So having this in mind is going to be important to eventually check whether this process is a martingale or a Markov chain. So before doing any calculation, let's think of whether it's a martingale, like intuitively, without using any math. Have in mind that I told you a martingale models a fair game, okay? And now you have a fair coin. In this case, we had a fair coin, but we don't really keep track of the amount of money you have if you play a fair game, okay? We just keep track of the coin flips. While here, you can rethink of your process as indeed the fortune of a gambler playing a fair game. So you can think of x0 as the amount of money you have if you go to the casino, okay, when you go to the casino. And then the game you are going to play consists in flipping a fair coin, okay, this coin. Each time you get heads, you win $1. Each time you get tails, you lose $1. That's indeed a fair game. And this process xn, instead of looking at it as the position of a particle, you can rethink of this process as the amount of money you have if you play this fair game. Okay? So it seems that intuitively the answer to martingale should be yes. This process is a martingale. Now, this is only the intuition. The way you prove that indeed this is a martingale, that's by using this decomposition. Remember that we saw in chapter 2 that the conditional expectation of a random variable given a sigma algebra is difficult to compute if your random variable is not measurable with respect to this sigma algebra or is not independent. You are in none of those two extreme cases, and so we don't really know what to do. But I also told you that the way you solve the problem typically is by writing your random variable as a sum or product, if possible, of a part that is fully known, measurable with respect to the sigma algebra, and a part that is independent of your sigma algebra. And that's what we can do in this case, and that's hidden behind this expression. So why is that? Well, to check whether we have a martingale, we need to look at quantity like that, expected value of xn plus 1 given fn. Now, what is xn plus 1? Xn plus 1 is obtained from xn by adding wn plus 1. So if you write xn plus 1 as xn plus wn plus 1, you indeed have like xn plus 1 written as a sum, xn that is fn measurable, that by definition at term n you know xn, and wn plus 1 that is indeed independent of fn. That's what we already had here. Wn plus 1 is independent of fn. So now the fn I'm using here, that's the one generated by this process, not wn, but still, if you know x0, x1 up to xn, this is not going to give you any information about the outcome of the next coin flip here. All right. So by using this decomposition, you can indeed prove that the process is a martingale. Okay, and here is the proof. You just start with the conditional expectation you are interested in. You look at expected value of xn plus 1 given fn. You rewrite xn plus 1 using this expression. You see that xn plus 1 is of the same form but plus wn plus 1. So that tells you that xn plus 1 is xn plus wn plus 1. Okay? Using the fact that the conditional expectation is linear, you can rewrite this expected value conditional expectation of the sum as a sum of the conditional expectation. But then the conditional expectation of xn given fn is just equal to xn. You are in the case of perfect information. If you know fn, you know xn. And another part that is a conditional expectation of wn plus 1 given fn, we already proved before that by independence, that's expected value of wn plus 1, which is 0. Okay? And so eventually, you can rewrite your conditional expectation as xn, that you know, plus an increment, the expected value of an increment that you do not know at all, independent of the past and the present, expected value of wn plus 1, but this is 0, and so you get that this is equal to xn. So indeed, we have a martingale. The conditional expectation of the future given past and present is equal to the value at the current time. So we have a martingale. Now, is it Markov or not? Again, you can use your intuition to see whether it's indeed Markov or not. Just look at this picture. It's clear that whether you are going to be at this integer or at this integer at time n plus 1 depends on whether you are here or somewhere else at time n. What matters is the position of the particle at time n. If you know the position of the particle at time n, you can say I'm going to be one less or one more at the next time step, both with probability 1/2. The past trajectory of the particle does not matter. So intuitively, this should be a Markov chain. Okay? The future, given past and present, should depend only on the present. The way you prove that is, again, to use this decomposition. So let's look at a typical event in the future at the next time step. So I'm looking at the probability that xn plus 1 equals x given fn. Okay? And we want to prove that this is also equal to the conditional probability of the same event, but given only the random variable xn. So for that, I'm using the same decomposition as before. Xn plus 1 is equal to xn plus wn plus 1. So this event is the same as the event that wn plus 1 equals x minus xn. Now, what is the probability that wn plus 1 is equal to x minus xn? Well, that should be 0 if this quantity is not equal to plus 1 or negative 1. Okay? This is, but at the opposite, this is equal to 1/2 if this quantity is equal to either plus 1 or negative 1. Saying that this is plus 1 or negative 1, that exactly means that the absolute value of x minus xn is equal to 1. Okay? And so eventually, we end up with the conditional probability of this event given fn, okay, is just equal to 1/2 times indicator function on the event that xn minus x, absolute value of that, is equal to 1. The fact that you can extract the 1/2 here is for the same reason as before. This wn plus 1 is independent of fn, and so you have this unconditional probability, just probability that wn plus 1 is equal to plus 1 or negative 1. Okay? So, probability that xn plus 1 equals x given fn is equal to 1/2 times the indicator function on the event that absolute value of xn minus x equals 1. And at this point, you can conclude that the process is indeed a Markov chain. So this is a technique that we use a lot to prove that processes are Markov. You see that this function here, this expression here, is a function of xn. Okay? It's of the form f of xn, where f of y is equal to 1/2 indicator function of absolute value of y minus x equals 1. This function f is measurable, okay? And so this expression, which is f of xn, because f is measurable, this function f of xn is xn measurable, okay? And because it's xn measurable, you can basically conclude that this conditional probability is the same as the conditional probability of the same event, but given only xn. That's how you prove that a process is Markov. You start with this conditional probability given the past and present, given fn. If you can write this random variable using only xn and not xn minus 1, xn minus 2, and so on, then that's it. That means that this conditional probability is xn measurable, and so can be written in this form, and so that shows that the process is a Markov chain. So now we have an example of process that is both a martingale and a Markov chain. So this example shows that Markov and martingales do not exclude each other. Now let's look at our third example. That's the Belling random walk. That's a nice generalization of the concept of symmetric random walk, but much more realistic in the context of games of chance. So here is the definition of the process. I'm going to now call the process yn. It's basically the same as the previous process we saw, xn. You play a game, the game is fair, you flip a fair coin. Each time you get heads, you win. Each time you get tails, you lose. Except that now, instead of betting only $1 at each game, you can choose your bet. And we assume that the bet is not fixed from the beginning. It doesn't have to be deterministic. It can be random. You can choose the bet based on the past. All right. So more precisely, yn is going to be the fortune at time n, your fortune at time n, when you win or lose the bet if the coin comes up heads or tails. So you win for heads, you lose for tails, the coin is fair. And we assume that the bet is called Bn, that's a random variable, that's how much money you bet at the nth coin flip. And we are going to assume that Bn is Fn minus 1 measurable. So why this assumption makes sense? Well, let's assume that Bn is Fn measurable for a minute. That would mean that at the time you decide Bn, or the information you use to decide Bn is the sigma algebra Fn. Then in this case, that would mean that how much money you bet on the nth coin flip depends on the outcome of this coin flip. And of course, that's not what happens in practice. In practice, when you go to a casino, you have to bet before you know the outcomes of the game. If you wait until the game is done to bet, that's basically cheating. You just bet a lot of money each time you win, and you bet nothing each time you lose. That's not the way it works. And so that's why we assume that this random variable Bn is Fn minus 1 measurable, which models the fact that you bet before the coin flip, not after. Alright, so that defines the process. Here we have again a picture of the process that looks like the same one as for the process Xn, except that now jumps can be of any different size. So let's assume that you have yn dollars at time n. That means that the amount of money you have is here. And then let's say that for the next coin flip, the next game, number n plus 1, you decide to bet $3. Then with probability 1/2, your fortune is going to be equal to yn plus bn plus 1, yn plus 3, or with probability 1/2 you lose, and your fortune is going to be yn minus bn plus 1, that's yn minus 3. Alright, so like before, you can replace those 1/2 by heads and tails, showing, like underlining the connection between this process and the first process we saw, the process Wn, that is this sequence of independent coin flips. So, same question as before, is this process a martingale or is it a Markov chain? So, first, is it a martingale? Well, it seems that it doesn't matter how much you bet, because the game is fair. You should have a martingale, even if you can choose how much money you have to bet. Before you bet, before you know the outcome of the game, then that should not change the expected value of your winning, the expected value of your of how much money you win at each game should again be 0. So we should have a martingale that's still a fair game. All right. So how can we prove that? Well, the trick is the same as for the process Xn. You see that yn plus 1 depends on the past, like the amount of money you have at time n, but also some kind of increment that is given by the outcome of Wn plus 1, whether you win or lose. So you can basically split your random variable yn plus 1 into a part that is fully known, which is the amount of money you have right now, plus a part that is independent of the past, including the present, which is Wn plus 1. And using this trick, we are able to prove that the process is a martingale. So in this case, the way you can write yn using the wn, but also using the bn is basically as follows. Okay, so notice that if you take b1, b2 up to bn equals 1, meaning you always bet $1, then you are back to the symmetric random walk we just saw, and indeed you get that the amount of money you have at time n after playing n games is the amount of money you have at time 0 when you enter the casino, plus the sum W1 plus W2 up to Wn. Here, the decomposition is the same, except that you have to add those weights B1, B2 up to Bn. So you add some weights in front of your Wi that are random -1s or +1s that corresponds to how much money you bet. So for instance, let's assume that you go to the casino with $0 and you are going to bet B1 at the first game, okay? So then if you win the first game, that means W1 equals 1. Then in this case, the amount of money you have after the first game is Y0 plus B1. Indeed, that's the amount of money you had when you enter the casino plus your bet. Or you lose, that means that W1 is equal to -1, you get takes. And then in this case, this W1 is -1, and so your amount of money at time 1 after playing one game is W0 minus B1. That's the amount of money you had at time 0 when you enter the casino, minus whatever you bet at the first game. Okay? And then you can continue like that. You have the same expression as for xn, but again with those weights in front of your random -1 plus 1 that corresponds to the bet. So indeed, yn can be expressed as that. Those two expressions are equal in this solution. That's what we are going to use to prove that the process is indeed a martingale. This expression also implies that to go from yn to yn plus 1, you have to add bn plus 1 times wn plus 1. And then we are going to have a decomposition of yn plus 1 using yn, which is known, bn plus 1, which in this case is known because you have to choose your bet before the game, and a wn plus 1, which is independent. So we are able again to break down the amount of money you have at time n plus 1, which is random, as sum and products of random variables that are fully known or independent of past and present. So more precisely, we have the following, and here I'm going to use two of the properties we saw in chapter 2. We start with this expression to prove that we have a martingale. We look at the conditional expectation of yn plus 1 given fn. Now fn is not the same as before. That's the filtration generated by the process yn. That's the natural filtration of the process yn. Then we decompose, like I just said, yn plus 1 as yn, whatever amount of dollar you have right now, plus bn plus 1, whatever you want to bet at the next game, times wn plus 1, plus or minus 1, depending on whether you win or lose. Now, notice that yn is fn measurable, so it's fully known. bn plus 1 also is fn measurable. That's the condition here. We assume that for all n, bn is fn minus 1 measurable, so in particular, bn plus 1 is fn measurable. So why is that? Well, that means that your decision of betting bn plus 1 at the coin flip number n plus 1 should be based on the information before that. Okay? So that's based on your knowledge of fn. So bn plus 1 is fn measurable, but same reason as before, wn plus 1 is independent of fn. Okay? It doesn't matter what happened in the past, including the present. The next coin flip is not going to change depending on this information. That's just something completely in the future, completely independent. Right, so that means that we have two parts that are fully known, they are Fn measurable, and we have one part here, Wn plus 1, that is independent of Fn. So we are in the right context where we were able to decompose our random variable into pieces that are fully known, perfect information, and pieces that are independent of past and present, that's no information. All right, so using the fact that the conditional expectation is linear, you can again split that into a sum of two conditional expectations and then remove your yn from the conditional expectation because that's Fn measurable. But then the second term is going to be a conditional expectation of Bn plus 1 times Wn plus 1 given Fn. We saw in chapter 2 that the conditional expectation of a product of two random variables given a sigma algebra is just equal to the first random variable times the expected value of the second random variable when Bn plus 1 is Fn measurable and Wn plus 1 is independent of Fn. So the trick we used previously for a sum of random variable also works for a product. All right? So eventually we end up with this expression. The conditional expectation of the amount of money you have at time n plus 1 given your knowledge of the past is equal to whatever amount of money you have right now plus Bn plus 1, which is random but that's something you decide at time n, okay, times the expected value of Wn plus 1. Wn plus 1 is unknown, that's in the future. You can only look at the expected value of that. Okay, again, we use the fact that expected value of Wn in general is equal to 0. Remember, Wn is equal to plus 1 or negative 1 with the same probability 1/2. And so the expected value of Wn is 0. And so eventually you end up with yn plus Bn plus 1 times 0, that's equal to yn. That shows that the process is indeed a martingale. So eventually you see that even if you make your bet random, okay, you can choose your bet and those bets can depend on all the past, okay? So based on your information of all the past, then that's not going to help you win more money. It doesn't matter what happened in the past. This is still a fair game, you still have a martingale. Alright, so now, is it a Markov chain or not? Well, the answer is it depends. It depends on how you choose the Bn. We just saw the example of the symmetric random walk on the integers. That's the special case where all the Bn here are equal to 1. And we saw that in this case, the process is a Markov chain. Now, in general, if you fix all the Bn to have like some specific values, so basically that can be any possible sequence, but it has to be deterministic, you can again prove that the process is a Markov chain. But if you really make the Bn random based on the past, then you can create a process that is not a Markov chain. And that's what I want to do here, to be able to prove that we have an example of process that is a martingale but not a Markov chain, so martingales does not imply Markov. Right, so how can we do this? Well, we need to create a situation where those Bn are not going to only depend on the money you have right now, but on the money you had in the past. And so one way to do that is by including some kind of psychological component in the process, and let's say do the following. I'm going to fix two numbers, they are deterministic, A and B. A is larger than B, and they are both positive. Let's assume, to make things simple, that A and B are integers. That corresponds to two possible bets. At each game, you can bet A or you can bet B. what you are going to choose between A and B depends on whether you won the previous game or not. Okay? So let's assume that you bet A, which is the larger bet. After each win, that's kind of modeling the fact that you feel lucky. But at the opposite, you bet B, the smaller bet, after each loss. So that means that you feel unlucky. So of course, we know that this idea of being lucky or unlucky is just some idea we have in our mind, but that doesn't really make sense in the sense that it doesn't matter whether we won a lot in the past, still at the next game we win with probability 1/2, and even if we lost a lot in the past, we still win in the future with probability 1/2. Whatever happens in the past is not going to change your probability of winning in the future. Still, in our mind, we have this feeling of being lucky or being unlucky, even if this type of behavior is not really rational for a mathematician. That's still something that makes sense, is realistic, and that's kind of the way we behave. So let's do this. And so why intuitively this example is going, this particular case of choosing Bn equal to A or B, depending on whether we won or lost the previous game, well, that's because the bet A or B is not going to depend on the next bet is not going to depend on how much money we have right now, but it's going to depend on how much money we have right now compared to the amount of money we had at the previous time step. And so eventually we should end up with a conditional probability with respect to Fn that should depend not only on Yn, but on Yn and Yn minus 1. That's not a function of only Yn, and so that's not Yn measurable. That's how we produce our counterexample. Example of process that is a martingale, fair game, but not a Markov chain. There is no loss of memory. There is a short time memory where you bet based on the previous time step, the previous two time steps, basically. So before we prove that, I just want to show you a picture of what the process can look like. Here I have a sample path or realization of the betting random walk that I just defined with A equals 4 and B equals 1. That means that each time you lose at the next game, you are going to bet $1, but each time you win at the next game, you are going to bet $4. Okay? Instead of drawing the trajectory using the same color, I have a mixture of black and gray here. All the gray shows all the jump of length $1. Okay? And all the black shows the jump of length $4. And if you look very carefully, you will see that each time your sample path goes down, then the next segment in your sample path is going to be gray, because after each loss you bet only $1. At the opposite, each time your sample path goes up, the next jump is going to be a black jump. Okay, so here in the picture you see basically all the black parts are when you bet $4, and all the gray part is when you bet $1. It seems that we have more black than gray. That doesn't mean that we win more often than we lose. It's just that black corresponds to a jump of length 4 versus a jump of length 1, and so it seems that we have more black, but in fact, on average, the number of black jumps of length 4 is the same as the number of jumps of length 1 in gray. Alright, so how do we prove that this process, we know already that it's a martingale, how do we prove that this process is a Markov chain? Well, that's exactly using the trick I just told you. We are going to look at the conditional probability of a typical event in the future, given the past. And we are going to, writing more in detail this expression, we are going to realize that this conditional probability is in fact a function of yn and yn minus 1. And so the future, given the past including the present, the future depends on not only the present but also the previous time step. So it depends a little bit on the past. That's why we don't have a Markov chain. The way you write that explicitly is as follows. Let's look at a typical event in the future. So if you have yn dollar right now, the amount of money you can have after the next game is yn plus a, or yn minus a, or yn plus b, or yn minus b. Okay? I'm just taking one of the four events. Let's look at the probability that yn plus 1 is equal to yn plus a, given the past including the present. So what does it mean that yn plus 1 equals yn plus a? That means that first you win because you have a plus. That means that at game n plus 1 you win. So wn plus 1 should be equal to 1. And 2, that means also that at this game you bet a, okay? And so that means that you won also the previous game. So that's basically the event that you win twice in a row. Basically, you just won and you are going to win again. All right. So we can express that by saying that this is the probability that wn plus 1 equals 1. That explains the plus here. That means that you win at this time n plus 1. And because you want to win a dollars, that means that your bet should be equal to a. bn plus 1 is equal to a. Then, next step, you are going to use again the fact that yn plus 1, okay, is independent of fn. At the opposite, bn plus 1 is fn measurable. So this conditional probability of yn plus 1 equals 1 given fn, that's the same as the probability that yn plus 1 equals 1 without the conditioning. At the opposite, this part is fully known, okay? So you can again think of the probability of an event as the expected value of the indicator function. Write this conditional probability, which is probability of an intersection of two events, as the conditional expectation of the indicator function on the event wn plus 1 equals 1 times indicator function on the event bn plus 1 equals a, and use the same trick as here to go from this expression to this one, and say that because this event is independent of fn, but at the opposite, this event is fn measurable, you end up with exactly this. So eventually you get expected value of the indicator function that's exactly what I explained, sorry. So you can decompose like that, and then that's this step that I want to look at. Eventually you have a product of two random variables. This one is is independent of fn, this one is fn measurable, and so you can split things exactly like we did here, and say that this is just the unconditional expectation of this indicator function, which is the probability that yn plus 1 equals 1. The other part is just a random variable fn measurable that can go outside the expected value, so that just indicator function on the event bn plus 1 equals a. Now, what is the next step? Well, probably that wn plus 1 equals 1, because we use a fair coin, again, that's going to be 1/2. So this probability is just 1/2. What about this indicator function? We have a bn plus 1. This is not our process. Bn plus 1 is just some process in the background, but our actual process that we are looking at is wn. So we need to rewrite this event, but using wn. So what does it mean that bn plus 1 equals a? that means that at game n plus 1 we bet $8, which means that we won the previous game, okay? And so it means also that the amount of money we have at time n, yn, should be larger than the amount of money we had at time n minus 1, which is yn minus 1. And so you can replace this event by the event that, that basically wn equals 1, which is the same as yn strictly larger than yn minus 1. Okay? So to bet A at game n plus 1, you need to win the previous game, which is exactly wn equals 1, the event wn equals 1, but wn equals 1 means that from time n plus minus 1 to time n, you increase the amount of money you have, and so that's exactly the event that yn is strictly larger than yn minus 1. Alright, so to recap, we start with probability of a typical event in the future at the next time step, given past and present, and we end up with a function of the two random variables, yn and yn minus 1. So this function here is not a function of only yn. You cannot write this as using only yn. So this conditional probability, in fact, is not yn measurable. And so that means that the process is not a Markov chain. Okay? So this example shows or gives you an example of stochastic process that is a martingale but not a Markov chain. So martingale does not imply Markov. To conclude this video, let's look at our last example of stochastic process that I'm calling the two-coin process. That's basically the same as the first process we saw, this sequence of independent coin flips, except that instead of using one fair coin, we are now going to use two biased coins. So the process more precisely is here. I'm going to call it Zn, and exactly like for the process Wn we saw at the beginning, Zn is equal to 1 or negative 1, depending on whether we get heads or tails at step n, at the nth coin flip. Except that the process in the background is defined by this procedure here. So we have two coins, coin 1 and coin 2. We are going to assume that coin 1 comes up heads with probability 1/3, while coin 2 comes up heads with probability 2/3. Alright? And whether we use coin 1 or coin 2 at any given step depends on the previous two outcomes. So more precisely, each time the previous two outcomes match, meaning that we get heads twice in a row or tails twice in a row, at the next coin flip we are going to use coin 1. Otherwise, we use coin 2, meaning that each time we get heads and then tails, or tails and then heads, we use coin 2. Alright, so of course, we can only follow this rule if we already flipped a coin twice, and so that cannot be the rule at the very beginning. To define the process, we need some initial condition, and this initial condition can be whatever. Let's choose that we flip coin 1 twice. Okay? We start the process by flipping coin 1 twice, then at the third coin flip, we already had two coin flips before, and we can follow this rule. Alright, so that's the process. So in this case, we can guess whether this process is a martingale or not, and is a Markov chain or not. It turns out that this process is not going to be a martingale. The reasons are the same as before here. Here we do not have a fair game. We do not keep track of the fortune of a gambler playing a fair game, or even an unfair, favorable or unfavorable game. These are just coin flip going from -1 plus 1, and so for the same reason as here, we are not going to have a martingale, or a sub-martingale, or a super martingale. Then, is it a Markov chain or not? The answer is no, and now the reason is the same as for the betting random walk. for the Benning random walk, we saw that we do not have a martingale because how much money we bet on a game depends on the comparison between the previous two amount of dollars we had, whether we won or lost the previous game. Here, that's kind of the same reason. The conditional probability of an event in the future given past and present is not going to depend only on Zn, that's also going to depend on Zn minus 1, because whether we use coin 1 or coin 2 depends on the previous two coin flips. So Zn and Zn minus 1, not just Zn. Another important information in this process, like the process is designed so that we do not have a Markov chain, is also the fact that coin 1 and coin 2 do not come up heads with the same probability. Okay? So depending on the previous two outcomes, we are going to use coin 1 and coin 2. But depending on the coin we use, we are going to have heads or tails with different probabilities. So that's the combination of those two things that are important to deduce that we don't have a Markov chain. Okay, so to write that into equations, the first step is to understand a little bit better our process at the next time step, so Zn plus 1. So let's look at the probability mass function of Zn plus 1. That's a Bernoulli random variable equal to plus 1 or negative 1, but with different probabilities depending on the previous two outcomes. And so eventually, you can just rewrite those rules that are written in English, but now in equation that just says that if Zn equals Zn minus 1, meaning that the previous two outcomes match, in this case, we use coin 1, and coin 1 comes up heads with probability 1/3. So that gives you this probability mass function. Probability that Zn plus 1 equals 1, heads is 1/3, and so the probability that Zn plus 1 equals negative 1, tails is equal to 2/3. At the opposite, if Zn is different from Zn minus 1, that means that we are in the second case here where the previous two outcomes do not match. In this case, we use coin 2, but coin 2 comes up heads with probability 2/3, which tells us that the probability that Zn plus 1 equals plus 1, heads, is equal to 2/3. At the opposite, the probability that Zn plus 1 is equal to negative 1, tails, is equal to 1/3. So eventually you see that the expression of the probability mass function of Zn is kind of reverse. You have a 1/3, 2/3 here, but a 2/3, 1/3 here, depending on the previous two outcomes. All right, so now how do we prove that we have a martingale, or that we do not have a martingale and that we do not have a Markov chain? That's again by looking at conditional expectation and conditional probability. I'm going to skip some steps because we already saw that several times. So first, to prove that the process is not a martingale, we are going to use the fact that Zn and Zn minus 1 are Fn measurable, but then at the opposite, the outcomes of the coin flip number n plus 1, even if it depends on which coin we are using, that's independent of the past, okay, of past and present. So we are dealing again with some Zn plus 1, okay, that can have two different probability mass functions depending on the past, but except for that, if you know this or that, then whether you get a plus 1 or a minus 1 is independent of past and present. At the opposite, like I wrote here, Zn and Zn minus 1 are Fn measurable. So that's the way you can break down Zn plus 1 into a part that is independent of the past and a part that is measurable with respect to Fn. And eventually, you get that the conditional expectation of Zn plus 1 given Fn is equal to negative 1/3 times the indicator function on the event Zn equals Zn minus 1 plus 1/3 times the indicator function on the event that Zn is different from Zn minus 1. This comes from just those expressions here. On the event that Zn equals Zn minus 1, the probability mass function of Zn plus 1 is given by that. And in this case, the expected value, the unconditional expected value of Zn plus 1 is equal to plus 1 times 1/3 minus 1 times 2/3. That gives you your minus 1/3 here. Same story for the second term. On the event that Zn is different from Zn minus 1, you are in this case, you have previous two outcomes do not match. The probability mass function of Zn plus 1 is given by this. And so in this case, the unconditional expected value of Zn plus 1 is equal to 1 times 2/3 minus 1 times 1/3. That gives you your plus 1/3 here. So that's how you read this. Because you look at the conditional expectation given Fn, okay, and because Zn and Zn minus 1 are Fn measurable, you can say that the conditional expectation of Zn plus 1 given Fn, what you expect at the next time step, is going to be negative 1/3 on the event that Zn is equal to Zn minus 1, but plus 1/3 on the event that Zn is different from Zn minus 1. Notice that those two random variables are indeed Fn measurable. Okay? Now, notice also that this event and this event are complement of each other. So that means that if this indicator function is 1, then this one is 0. If this one is 1, then this one is 0. Eventually, you end up with a random variable that can only be equal to negative 1/3 or plus 1/3. Zn is never equal to any of those two values. Zn can only be equal to plus 1 or negative 1. And so that shows exactly like for the first example that the process is not a martingale. Okay? Notice also that if Zn is equal to negative 1, then this conditional expectation, no matter what the outcome, this conditional expectation is always going to be larger than Zn. At the opposite, if Zn is equal to plus 1, this conditional expectation is going to be always less than Zn, which shows an even stronger result, the fact that Zn is not either a sub-martingale or a super-martingale. Alright, so that shows that the process is not a martingale. To prove that the process is not Markov, so the intuition, again, like I said, is the same as for the Belling random walk. The probability that Zn plus 1 equals 1, for instance, is going to depend on the coin you use at that time, but the coin you use at that time depends on the previous two outcomes, on the previous two coin flips, and so the conditional probability of Zn plus 1 equals 1 given Fn is not going to be a function of only Zn, that's going to be a function of Zn and Zn minus 1. And that's enough to prove that the process is not Markov. So more precisely, we can do the following calculation. Again, here, I'm skipping a few steps implicitly in the background to get this equation here. What I'm using is the fact that, so if Zn equals Zn minus 1, we are in the case of a match, and in this case, the probability that Zn plus 1 equals 1 is 1/3. That's where this 1/3 comes from. At the opposite, if Zn is different from Zn minus 1, the probability mass function is given by this expression. In this case, Zn plus 1 is equal to plus 1 with probability 2/3. That's where this 2/3 comes from. The fact that this conditional probability is indeed equal to this random variable, okay, is due, and I skip a few steps, but again, to the fact that Zn and Zn minus 1 are Fn measurable, and so such an indicator function in a conditional expectation here can get out of the conditional expectation because we have something that is Fn measurable. The 1/3, 2/3 are here because given this or that, the probability that Zn plus 1 is equal to plus or minus 1 does not depend on the past. Okay? Once this is fixed, you have this expression. Again, I'm skipping a few steps, but you can prove this. That kind of makes sense. Okay? It says that the probability that you get heads at the next outcome is going to be 1/3 if we had a match, or 2/3 if we didn't have a match for the previous two outcomes. Okay, so now you see that you have a function now that depends on Zn and Zn minus 1, not only Zn. You can turn it the way you want. You realize that you cannot get rid of your Zn minus 1. That's a true function of those two random variables, not only Zn. And so that shows that this conditional expectation given Fn is not Zn measurable. And so that shows that the process is not a Markov chain. Okay? So this stochastic process gives you a fourth example like that we did not see before of a stochastic process that is not a martingale and not a Markov chain. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 5 of my textbook. That's a chapter about martingale theory. In particular, we are going to prove the optional stopping theorem, upcross inequality, and martingale convergence theorem, as well as other theorems related to what we call regular martingales and reverse martingales. Then after combining reverse martingales and something that we call Kolmogorov 0,1 law, we'll be able to end up with a complete proof of the strong law of large number, even when dealing with random variables that have an infinite variance.